Settle in and let your breathing slow, just a little. Picture a quiet stretch of the Yucatán coast at night, where warm air hangs close and the waves keep a lazy rhythm. The towns are dim, the roads are empty, and the ground looks perfectly ordinary. Flat limestone, pale sand, nothing dramatic. But the earth is good at keeping secrets. It hides them under smooth layers, and it waits for someone patient enough to notice the tiniest pattern that does not belong. Tonight, with the Sleepless Scientist keeping you company, you are going to follow those small, boring clues, old maps, faint circles, gentle measurements, until they lead to something enormous sleeping beneath your feet. You are not standing on a crater rim. There is no dramatic bowl of rock, no jagged ring of mountains, no helpful sign that says, "Welcome to the place where everything changed." Instead, you are standing on a polite disguise, a sheet of pale limestone laid down like fresh paint. The Yucatan is like that. It is smooth, stubbornly flat, and almost offensively calm. And the trick is that geology does not always shout. Sometimes it whispers through paperwork. So imagine yourself in a small office decades ago, where the most exciting thing in the room is a stack of maps, not treasure maps, not pirate maps. Industrial maps made for oil exploration, for groundwater studies, for the simple business of finding resources inside an inconvenient planet. The first clues to Chicxulub were not found by someone heroically kicking at rocks on a jungle trail. They were found the way many Earth secrets are found, by people doing their day jobs and noticing the numbers looked slightly wrong. You are tracing a finger along a printed line, and it bends in a way it should not. A contour on a map curls into an almost circle, not a perfect circle, not a cartoon ring, just a suggestion of one, like a coffee stain that refuses to fade. And you tell yourself it is nothing, because circles are suspicious. Nature likes mess. It likes torn edges and uneven shapes. But then you see it again in a different data set, from a different year, made by a different group. A curve, a rim, a faint outline that does not match the surface landscape. Out here, above the quiet coastline, your eyes see nothing. But down below, the rocks remember. The earliest hints came from measurements that feel almost boring when you describe them. Gravity surveys, magnetic surveys, the kind of thing that sounds like homework. But gravity is just the Earth holding you, with a grip that changes slightly from place to place. Not enough for you to feel it in your bones. Enough for a sensitive instrument to notice, like a scale that can detect a single extra coin in your pocket. So you drive slow roads, or you fly straight lines, and you measure the pull. Heavier here, lighter there, a subtle pattern repeating. Now, magnetism is similar. The planet's quiet, invisible habit of behaving like a giant bar magnet. Rocks can carry magnetic fingerprints depending on what minerals they hold and how they cooled long ago. When you map magnetism, you are mapping the ghost of ancient heat. Oil companies loved these surveys, not because they cared about ancient disasters, because they cared about structure. Oil and gas collect in traps, folds, domes, broken layers. To find those traps, you map what you cannot see. You become an expert in invisible shapes. And so, without trying to solve the biggest murder mystery in Earth history, people began drawing lines that curved. They did not call it Chicxulub yet. They just saw a ring. You can picture it as a sleepy kind of revelation. No lightning strike. Just a map on a table and someone leaning closer and someone else saying quietly, "That looks like a circle." A ring shape underground is rarely a coincidence. It suggests something that pushed outward from a center, something that cracked rock in a round pattern, the way ice cracks around a stone. But before you get excited, the earth tries to make you feel foolish. Because there are other ways to make rings. Salt can rise like slow toothpaste, forming domes. Volcanoes can collapse into calderas. Tectonic forces can bend layers into broad arcs. Geology has many tools for drawing circles, and none of them come with labels. So the ring sits there, in the data, like an unfinished sentence. And people keep working. They keep drilling wells for practical reasons, and they keep writing reports with practical titles. And this is the part that always amuses me in a tired way. The planet's greatest plot twist was hiding inside filing cabinets. Because oil exploration does not just create maps, it creates cores and cuttings and logs, boring words for extremely intimate contact with deep rock. A drill turns and turns and turns, and the earth gives up crumbs. Those crumbs are bagged, labeled, and stored. Sometimes they are studied. Sometimes they are forgotten. And one day, a forgotten box becomes important because someone asks a different question. What could make a perfect wound like that? To answer, you have to stop thinking like a human for a moment. You have to think like an impact. An impact is not a crash, the way a car crashes. It is not two objects meeting. It is energy arriving too quickly. A big asteroid does not simply hit. It delivers a quantity of motion so violent that rock behaves like liquid briefly, and then like vapor briefly, and then like broken memory for a long time. You do not need to picture the dinosaur apocalypse right now. You can keep it quiet. Just imagine the physics, stripped of drama. A space rock arrives at tens of thousands of miles per hour. The air in front of it compresses and heats. The ground cannot move out of the way, so it fails. In less time than it takes to blink, limestone becomes something else. It shatters. It melts. It is squeezed so hard that its minerals are rearranged. There are certain fingerprints that impacts leave behind, and they are strangely tender in a scientific way, because they are signs of a moment so extreme that the rocks keep a private diary entry forever. One classic sign is shattered rock, not just cracked, but fractured into a chaotic mosaic. Geologists call some of these deposits breccias, a word that sounds like a cough. In human terms, it means rocks that have been through something and never fully recovered. Another sign is melt. Not lava from a volcano, but impact melt. Rock heated so fast it does not have time to behave politely. It becomes glassy, or fine-grained, or mixed with fragments like a poorly made soup. And then there are the minerals that form under shock. Quartz, for example, can carry tiny features called shocked quartz, where its internal structure shows it was squeezed brutally. It is like wood grain after a storm bends a tree, except it happened in an instant. There are also tiny glass beads, sometimes formed from splashed molten material that cooled in flight. They can be microscopic, like glitter you never asked for, sprinkled through sediments far away. These are not things you see easily on the surface, especially not on the Yucatan. The crater is buried and the surface is smooth, so the evidence had to be collected indirectly, like listening to a sealed room through a wall. That is why the ring in the data mattered. It was not proof. It was an invitation to look closer. And for a long time, people did not connect it to the dinosaur extinction. They were working different problems. They were measuring gravity because gravity helps you find structures. They were drilling because drilling finds oil. The crater was just there, quietly cooperating. Then, elsewhere, another clue was already waiting in the rocks of the world. A thin layer at the boundary between the age of dinosaurs and the age after. A boundary that geologists had been studying for reasons that had nothing to do with craters at first. In some places, that boundary looks like a modest smear of clay. Not impressive. Just a thin line in a cliff face, a slight change in color, a small pause in the story. But it carried something odd, an element that is rare in Earth's crust and more common in meteorites: iridium. A word that sounds expensive. And in a way, it is. Not because it buys you anything useful, but because it buys you a hypothesis. If you find more iridium than you expect, you start asking why. If you find it in the same time layer around the world, you start suspecting a global event. This is where the story becomes one of slow alignment. Not one genius moment, but many partial truths drifting toward each other, like continents, a ring in geophysical data, shock features in rock, a global boundary layer with unusual chemistry. All of them hinting that something big happened, and that it happened at a particular time. But Chicxulub still had to be confirmed, like any shy suspect. The Earth does not accept accusations without evidence. So you go back to the Yucatan, back to the flat limestone, back to the coastline that looks like it has never experienced drama in its life. And you ask a quiet question: where exactly is the center? Chicxulub, as a name, comes from a town near the crater's center. It is a human name for a non-human event, a little label pinned to something that does not care. If you could peel the limestone away, you would find a complex crater, not just a simple bowl, but a structure with rings and a central uplift shaped by the rebound of the crust after the blow. Because impacts do not just dig holes, they also cause the ground to spring back like a mattress punched by a fist. But you cannot peel the earth like an orange, so you use indirect senses. You read gravity anomalies, places where the gravitational pull is slightly different because rock density is different. Impact structures can have dense melt rocks, broken zones, and uplifted material. Those differences alter gravity in a way that can, with enough data, sketch an outline. You read magnetic anomalies, places where the magnetic field is slightly different because certain rocks carry certain magnetic minerals. Impact heat can reset magnetic signatures, like erasing and rewriting a tape. And you drill. Drilling is slow and loud and not romantic. A rig groans. Mud circulates. Bits wear down. People drink coffee and check gauges and do the same motions again and again. But what comes out of the ground is a kind of time candle, a long cylinder of rock that has been sleeping untouched for millions of years. You lift it into the light, and it looks disappointingly ordinary at first. Beige, gray, white. Limestone, more limestone, chalky textures that could put you to sleep twice. Then, if you are patient, you notice the interruptions. A layer that is darker, a layer with angular fragments, a texture that looks crushed or melted or mixed. A geologist logging core is doing something almost meditative. You hold the cylinder, you note the grain size, you note the color, you note the boundary between one layer and the next, and the rock, if you listen properly, begins to tell you when the quiet was broken. In the Chicxulub region, drill cores encountered unusual rocks that did not fit the simple story of calm marine limestone. There were breccias, chaotic mixtures that suggested violence. There were melt rocks that hinted at sudden heat. And there were signs that the structure was circular and vast. Over time, the circle became harder to ignore. Not a circle drawn by a human, but a scar that shaped the subsurface. This is the part where people sometimes expect a single discovery moment. Someone shouting, "We found it." But reality is softer and more bureaucratic. The crater was recognized through a gradual process involving multiple scientists, multiple data sets, and multiple reinterpretations of older work. Some early drilling in the region, done for oil, had already encountered strange rocks. But the significance was not fully appreciated at the time because data does not announce itself. It sits, it waits. And sometimes it takes decades for the right question to arrive. So picture yourself opening a report written in dry language. It describes a well, it lists depths, it mentions odd fragments, nothing dramatic. And then, because you now suspect an impact, those same boring descriptions transform. The fragments are not just inconvenient debris, they are impact breccia. The odd crystalline textures are not just weird, they are shock features. This is one of the quiet truths of science. Evidence can exist before its meaning does, which is comforting in a strange way. It means the world is full of answers you have not learned how to read yet. Not because they are hidden, but because you are still learning the alphabet. But then, gently, you also start to see why the crater stayed hidden for so long. Because the Earth is always tidying up after disasters. You might imagine a crater as a permanent wound, like a scar on skin. But Earth has no reason to keep its scars visible. It is an active planet with weather, water, tectonics, and time, all working together like an unfeeling cleaning crew. On land, craters erode. Wind and rain soften the rim, and rivers carve through the bowl. Given enough time, the crater becomes a vague depression, then a ring of hills, then a rumor. Under the sea, craters are buried. Sediment drifts down like slow snow. Shells accumulate. Mud settles. Layers build. Thin sheet after thin sheet until the sharp edges blur. The Yucatán, for much of its recent geological life, has been a warm, shallow marine platform. That is a calm way of saying it spent a lot of time underwater collecting carbonate sediments. Carbonate is the material of shells, corals, and tiny marine organisms that live and die and leave their calcium behind. Over millions of years, those remains become limestone. Smooth, pale, and thick. A blanket. So after the impact, after the chaos, after the long settling, the region returned to being a place where sediments quietly piled up. The crater's topography softened. its center filled. The sea came and went. The coastline shifted. Groundwater dissolved some layers and redeposited others. You can think of groundwater as the planet's slow internal breath. It moves through pores and cracks, dissolving minerals, carving caves, then leaving behind new crystals when conditions change. In the Yucatan, groundwater creates sinkholes called cenotes. They are beautiful. In a calm, dark way, circular openings into water-filled caves. And yes, even that can confuse the story. Because when you see circles on a map, you have to ask, is it a crater or is it karst? The landscape of dissolving limestone. Geology rarely gives you a single clean answer. It gives you overlapping processes stacked like blankets on blankets, which is why indirect measurements matter so much, because the surface is not honest. The surface is the last page of a book that has had previous chapters torn out and rewritten. So you learn to notice what is missing. A normal limestone platform has certain patterns and layers. A normal region has certain gravitational signatures. A normal magnetic field map has a certain texture. But at Chicxulub, the normal story is interrupted by a structure too large, too round, too distinct to be ignored forever. And once you accept that, you can start asking calmer questions. How big is it really? What does it look like underground? What rock types mark the boundary between the crater and the surrounding platform? How deep is the disturbed zone? Where is the central uplift? These questions are answered not by one heroic expedition, but by careful measurement and patient drilling. And that is why this story, for all its famous consequences, is strangely gentle. Because it is mostly about people reading, people comparing, people arguing politely over contour lines. And when you picture it like that, you can see the crater as it truly is, not as an apocalyptic symbol, but as a geological structure with a geometry, a density contrast, and a history, a hidden ring beneath a quiet coast. And as the shoreline fades into the dark, you notice the first kind of clue. Geology loves a pattern that should not be there. It starts, again, with data that feels too plain to matter. A gravity map made of subtle shades where a gentle circle appears in the values. A magnetic map where the textures shift around an unseen center. A set of well logs listing rock types and depths like a grocery receipt from the underworld. You follow the lines slowly, letting your mind drift with them. You notice how the anomalies form arcs, and how those arcs hint at something ring-shaped. In some cases, the ring is not one ring, but several. Complex impact craters can have multiple rings, created by the collapse of the crater walls and the rebound of deeper rock. It is almost like the Earth struck hard, tried to settle itself, and left ripples frozen in stone. The ring is not a crater rim you could hike. It is a boundary in physical properties, density, magnetism, rock fabric, a ring you can only see through instruments. And you, lying safely in bed, get to appreciate the absurdity. The most important circle in modern Earth history was discovered with the emotional intensity of bookkeeping. Congratulations, your planet is run by accountants with seismographs. Oil exploration also contributed another kind of clue, through seismic surveys. In a seismic survey, you send sound waves into the ground and you listen for echoes. The echoes return from different layers, depending on how hard or soft they are, how dense, how fractured. It is like tapping on a wall to find a hollow space, except the wall is miles thick and the tapping is done with controlled vibrations. The result is a cross-section image, a picture of subsurface layers that looks like smeared stripes. And in those stripes, sometimes you can see disruptions, layers bent downward, broken, or uplifted. In the Chicxulub area, seismic profiles revealed a structure consistent with a large crater. Rings, faults, and a central uplift were hinted at in the echoes. This is a good moment to remember how strange it is that sound can do that. A wave, a vibration, traveling through rock that has been buried since before humans existed. A temporary tremor, passing through ancient scars and returning with information. But even with seismic data, even with gravity, even with magnetics, the Earth does not hand you certainty for free. A ring could still be something else. In principle, a buried volcanic structure, a salt feature, a tectonic dome. So you need impact fingerprints. You need rocks that have been shocked, melted, shattered in a way that only an impact can easily explain. And that brings you back to cores and cuttings and thin sections under microscopes. A thin section is a slice of rock ground so thin that light passes through it. It is a delicate thing made from something that once resisted a drill bit. You place it under a microscope and suddenly the rock becomes a landscape of crystals, quartz grains, feldspar, tiny fragments, cement holding them together. And sometimes, inside a quartz grain, you see parallel lines, microscopic features that tell you the crystal was compressed beyond normal Earth processes. The rock does not scream about it. It just shows you, quietly, that it remembers. Once you have that, the circle becomes more than a circle. It becomes a crater. And once you have a crater, the next sleepy question is simple. What could make a perfect wound like that? You start by shrinking the problem down to something your sleepy human mind can hold. Not the extinction, not the drama, just the object itself, a chunk of rock and metal left over from planet building, wandering the solar system like a lost screw in a moving car. It does not hate you. It does not notice you. It is just following gravity, the way spilled water follows a floor. If you could stand beside it in space, you would be disappointed. No glow, no menace, no soundtrack. Just a dark shape turning slowly, cold enough to make a warm thought feel illegal. Then the orbit intersects Earth, and the boring object becomes a physics lesson with teeth. You do not experience the impact first. You experience the approach. The air in front of the asteroid compresses so violently that it heats up, not like a stove heating a pan, more like a bicycle pump heating your hand, except the hand is the atmosphere and the pump is fate. By the time the object is low enough to see, the sky is already doing its emergency procedures. A shock wave forms in the air, and the air itself becomes a furnace. The asteroid is not burning because it is on fire exactly. It is burning because it is bullying the air into becoming plasma. You think the air protects you from space. It does, most days. Tonight, it is also the thing that turns incoming rock into a blazing spear. And then there is the ground. You imagine the asteroid hitting like a hammer, a solid object slamming into a solid planet. But solids are only solids when the forces are polite. At impact speeds, rock does not get a chance to be rock. It becomes fluid for a moment, and then vapor, and then a spray of fragments that will spend the next few million years trying to look normal again. This is why impact craters are so distinctive. They are not dug like holes with shovels. They are made by a shock wave, a pressure pulse that moves faster than sound through rock, turning structure into chaos. So the first thing an impact leaves behind is not a pit, it is a shock. Picture the crust as a quiet library of minerals, stacked neatly on shelves. Now picture a pressure wave slamming through that library and making every book explode into confetti, while the shelves themselves melt. That wave radiates outward and downward. It compresses rock so hard that crystals deform in ways they normally never do. Quartz, the stubborn little mineral that shows up everywhere, is usually calm and orderly. But under an impact shock, quartz records thin parallel lines inside its grains. Those lines are called planar deformation features. That is a scientific phrase for the crystal got squeezed so hard it developed trauma stripes. And the beauty of it, the sleepy kind of beauty, is that these features can last. They are tiny, but they are durable. So when you pull up a core and you slice it into thin sections and you put it under a microscope, you are not just looking at minerals. You are reading a moment of impossible pressure frozen into a pattern. Other clues are more dramatic, even in stone. Some rocks become melt, not slow volcanic melt that sits and cools. Impact melt happens so quickly that it can trap fragments, bubbles, and weird textures, like a flash-frozen stew. You can get glassy material. You can get fine-grained rock that cooled too fast to grow big crystals. You can get mixtures where pieces of different rocks are suspended together because the impact was not picky. And then there are breccias. Breccia is what you get when rock is smashed and then glued back together. Angular fragments, sharp edges, jammed in a matrix like broken ceramic in wet cement. It is a deposit that says, something shattered this place, and then gravity and heat tried to clean up. At Chicxulub, there are thick sequences of impact breccias, including a famous one called suevite. Suevite is basically impact rubble with bits of melt mixed in, like a demolition site where some of the concrete also caught fire. That is the kind of rock that makes geologists sit up, even if they have been pretending to be bored for professional reasons. But your question is still, what could make a wound that wide? Chicxulub is roughly 100 miles across, give or take, depending on which ring you measure and how you define the edge. That is not a cute little crater. To make something like that, you need an impactor that is not a pebble. Most estimates put it around 6 to 10 miles wide, which sounds manageable until you remember this is not about size alone. It is about speed. A 6-mile object moving faster than a rifle bullet carries more energy than the human brain likes to picture. It is not just a crash. It is a transfer of planetary scale kinetic energy into heat, pressure, and motion. And the Earth responds by doing what any material does under sudden stress. It fails. It fractures. It rebounds. This is where crater geometry becomes a sleepy little puzzle. Small impacts make simple bowl craters, a neat depression with a raised rim. But when the crater gets large enough, the walls cannot hold their shape. They slump inward. The floor rebounds upward because the crust behaves like a shocked mattress. So you get a complex crater, a central uplift where deeper rock rises, a peak ring where a ring of uplifted material forms around the center, faults and terraces where the walls collapsed. At Chicxulub, seismic data and drilling suggest this kind of structure, with a peak ring buried under later sediments. And this matters because it gives you more targets to test. If you drill in the right place, you should find rocks that were lifted from depth. You should find shocked material. You should find melt and breccia in predictable patterns. It becomes less like guessing and more like checking a blueprint. This is how geology gets its confidence. Not by being dramatic, but by being consistent. You predict where the mesh should be. Then you drill and see if the planet agrees. And because the planet is never completely cooperative, you also keep asking whether anything else could mimic these signals. Volcanic calderas can make rings. Salt structures can make domes and circular patterns. Tectonics can fold and fault in ways that look rounded. But none of those processes, on their own, give you shocked quartz. None of them produce the same suite of high-pressure mineral transformations. Impacts can even create minerals that are effectively pressure fossils. Coastline and stishovite are high-pressure forms of silica. They are what quartz becomes when it is forced into a tighter crystal structure. It is like taking a comfortable chair and compressing it into a hard cube. Same material, different arrangement, created under conditions that normal crust does not enjoy. Finding those minerals is like finding a signature written in a handwriting only an impact uses. So, the answer to your question, the quiet answer, is that Chicxulub was made by an asteroid, or possibly a comet fragment, that arrived too fast for Earth to respond politely. And that is the end of the simple version. Because now, you have another question hiding under it. If impacts leave such distinctive fingerprints, why was Chicxulub not obvious immediately? Why did it take so long? The reason is not that the crater is subtle. The reason is that the crater is buried, disguised, and inconveniently placed. You are dealing with the Yucatán platform, a broad region of limestone built over long time. It is a place where the surface does not show you the deeper architecture. So, to understand why Chicxulub stayed hidden, you have to understand how a crater disappears without ever truly leaving. You begin with the moment after the impact. Not the fire, not the noise, just the aftermath, the slow return to geological routine. The crater is a fresh basin. Its walls are unstable. Loose debris slumps inward. Melt cools, water returns. If the crater is on land, rain and rivers start cutting it down. If the crater is near the coast, the sea moves in and out, filling it, draining it, filling it again. And if the crater is submerged, it becomes a natural sediment trap. Sediment loves low places. Mud, sand, shell fragments, all of it drifts and settles into depressions. The crater becomes a bowl that catches time. Each year, each storm, each slow bloom of marine life adds a dusting. Not enough to notice in a day. Enough to bury a mountain if you wait. The Yucatán, in particular, is built from carbonate sediments. Carbonate is what you get when warm, shallow seas produce enormous amounts of shell material. Tiny organisms make calcium carbonate structures. They live, they die, and their remains settle like pale snow. Over long spans, that snow compacts into limestone, layer after layer, bright and soft-looking even when it is hard. So Chicxulub did not stay as a fresh scar. It became a foundation, the crater filled with sediments and collapsed debris. Then it was draped with limestone. Then it was draped again, the surface smoothed out, like someone making a bed over a mess they do not want to talk about. And while the surface grew calm, water started doing what water always does. In limestone, it dissolved it. Groundwater moves through pores and fractures, picking up carbon dioxide from soil, becoming slightly eating carbonate rock. This is how you get karst landscapes, caves, sinkholes, underground rivers, and those famous Yucatán cenotes. And karst does something sneaky to crater detection. It makes circles. A sinkhole can be circular. A cenote can be circular. A field of collapsed caves can create circular patterns from above. So if you are looking at aerial photographs and you see rings and arcs, the planet is ready to gaslight you. That is not a crater, it says. That is just limestone doing limestone things. Which is why Chicxulub's discovery depended so heavily on geophysics. Gravity does not care about sinkholes. It cares about density contrasts at depth. Magnetism does not care about cenotes. It cares about minerals that were heated, shocked, and rearranged. Seismic waves do not care about pretty surface features. They care about buried boundaries, about broken zones, about the architecture under the blankets. This is the part where you start appreciating the Earth's talent for cover-ups. You think of geology as reading what is written, but much of it is reading what has been overwritten. Erosion removes, sedimentation adds, tectonics bends and breaks, water dissolves and redeposits. A crater is not just a hole, it is a disturbance in a dynamic system. Given enough time, the system absorbs the disturbance, and the crater becomes a quiet anomaly, detectable only if you know what to measure, and even then, only if you can afford to measure it. Which brings you back, gently, to the human side, not the dinosaurs, the geologists. Most of the data that first hinted at Chicxulub came from resource exploration. Oil, gas, groundwater, not from people searching for an extinction crater. This is one of those sardonic truths that keeps repeating across science. The big discoveries are often byproducts of someone trying to make payroll. A company pays for a seismic survey to find a reservoir. A crew collects gravity data to map a structure. A drill rig takes cores to test rock properties. And then, decades later, a scientist looks at that same information and says, "Wait, why is it circular?" In the Yucatan, a pair of geophysicists, Antonio Camargo and Glenn Penfield, were among the first to notice the ring-like gravity and magnetic anomalies in the late 1970s and early 1980s. They were working with data from the Mexican National Oil Company. They were not hunting the dinosaur killer. They were doing the patient, repetitive work of mapping subsurface structure. They saw the arc of anomalies. They traced it. They realized it might be a crater. And then, like many discoveries, it did not immediately change the world. Not because it was wrong, because it was stuck in the slow machinery of communication, access, and priorities. Data collected for industry is often proprietary. Reports can sit in archives. People move jobs. Interpretations get filed away. Meanwhile, in a different part of science, another line of evidence was building. The boundary layer, the iridium anomaly, the shocked quartz found in boundary sediments, the global distribution of a thin layer of ejecta. Different scientists, different tools, different questions. And then, eventually, those threads crossed. When you connect an impact crater to a global chemical signal, you start dealing with a local curiosity. You start dealing with an event that rearranged the biosphere. But you are not there yet. Not emotionally. Right now, you are still in the calm part of the story, where a crater is a structure, and structures can be measured. So you keep thinking about how to confirm it. You picture a drilling core again, because cores are the planet's most boring truth serum. A core comes up in segments. Long cylinders laid into boxes, row after row. Each segment labeled with depth, because depth is time, in a crude but useful way. The upper sections are young limestone, white, chalky, full of tiny fossil bits. You can almost smell the sea that made it, even though it is long gone. Then you go deeper, and the limestone changes. Different textures, different fossils, different shades of pale. And then, if you drilled in the right place, you hit the disturbed zone. The rock becomes fractured. It becomes mixed. It becomes less like a story and more like an argument. You find breccias, angular clasts, fragments of older rock trapped in a finer matrix. You find melt rock, darker, denser, sometimes with a glassy look. And in the lab, you find those tiny shock features. This is where the confirmation process becomes a slow stacking of small facts. Not one clue, but many. A circular gravity anomaly, a matching magnetic pattern, seismic reflections, showing a complex crater architecture, core samples with breccias and melt, microscopic shock features and quartz, geochemical signatures that suggest extraterrestrial material. Each one alone is interesting. Together, they become difficult to argue with. This is what it means to confirm something in geology. You cannot rerun the experiment. You cannot recreate an asteroid strike for ethical reasons and also budget reasons. So you do what you can. You compare, you map, you drill. You look for multiple independent lines of evidence that converge on the same story. And because the Earth is old and messy, convergence is the closest thing you get to certainty. While this was happening, the crater itself kept being quietly complicated. Chicxulub is not a simple structure with clean edges. It is buried under younger sediments, including those same carbonates that make the surface so calm. Parts of it are offshore. Parts of it are beneath towns and forests and farms. So mapping its full size and shape took time. Seismic lines had to be collected and reinterpreted. Gravity maps had to be refined. Magnetic data had to be corrected for all sorts of noise. Noise is the enemy of gentle discovery. Ships roll, instruments drift, Earth's magnetic field changes with time. Data is collected in different formats, with different resolutions, in different decades. So, you end up doing something deeply unromantic. You clean the data. You correct for regional trends. You remove artifacts. You align coordinate systems. You compare data sets that were never meant to be compared. It is like trying to assemble a quilt from scraps cut by different people in different centuries. But eventually, the image sharpens. A large circular structure centered near the town of Chicxulub. A multi-ring crater with a peak ring buried beneath a limestone blanket. A scar that matches the timing of the boundary event. And when you reach that point, you might think the story becomes loud. It does not. It becomes methodical. Because once a crater is identified, The next phase is to understand it in detail. How thick is the impact melt sheet? What is the composition of the breccias? How far did the shock damage extend? What were the target rocks? Target rocks matter because what you hit changes what you release. Chicxulub struck a region rich in carbonate and evaporite sediments. Carbonates are calcium carbonate. Evaporites can include gypsum and anhydrite, sulfates deposited when seawater evaporates. When you vaporize and heat those materials, you can release carbon dioxide and sulfur compounds, which means the environmental effects are not just about dust. They are about chemistry. But hold that thought for later. For now, you stay with the crater itself, the way it gets studied like a sleeping animal. One of the most famous modern efforts to understand Chicxulub involved drilling into the peak ring offshore through an international scientific program. The point was to sample rocks that were uplifted from depth and to understand how a large, complex crater forms. Peak rings are not intuitive. They are not just piles of debris. They are structural features created by the collapse and rebound during crater formation. In simplified terms, the impact excavates a cavity. The cavity is too big to be stable. Material slumps inward. Deep rock rebounds upward. The rebound overshoots and collapses outward. The result is a ring of uplifted rock, a kind of frozen wave in the crust. Drilling into that ring lets you test models of crater formation, and it lets you examine how rocks behave under extreme conditions. And when the cores come up, they often show fractured, altered rock with veins and breccias and signs of hydrothermal activity. Hydrothermal activity is one of those quietly important aftermaths. After a big impact, you have heat, melt sheets, hot fractured rock. Water moves through those fractures, driven by temperature gradients, like circulation in a radiator. This can create a hydrothermal system that lasts for thousands of years, sometimes longer. It alters minerals. It deposits new ones. It changes the chemistry of the rock. And in some impact craters, hydrothermal systems are considered potential habitats for microbial life. Not because the crater is friendly, because life is opportunistic. Give microbes heat, water, and chemical gradients, and they will show up like unwanted comments on a public post. So even in a story about destruction, there is a quieter story about aftermath and new niches, but you do not need to get sentimental about it. You can just note, calmly, that the Earth does not waste energy. A big impact creates heat. Heat drives fluids. Fluids alter rock. And those altered rocks become part of the signature geologists look for. So, the crater is not just a hole. It is a zone of altered crust with a long tail of consequences. Now, while you are still thinking about buried scars, it helps to imagine time as something physical, not years on a calendar. Layers. Picture sediments settling through water like dust through lamplight. A storm drops a slightly darker layer. A calm season drops a lighter one. A shift in sea level changes the grain size. The crater becomes a basin that collects these layers. As the basin fills, the surface becomes flatter, and when the basin is full enough, the next layers do not even hint at what is below. Eventually, the crater is just subsurface architecture. This is why the Yucatán looks so calm. It is not calm because nothing happened. It is calm because time is an excellent interior decorator. And because time is thorough, the crater's surface expression is minimal. You might see subtle patterns in groundwater flow. You might see arcs of sinkholes. You might see faint topographic differences, but you would not stand on the coast and point and say, "There it is." You would need instruments. You would need cores. You would need patience, which is why Chicxulub is such a perfect case study for how geology discovers things, not with hero shots, with boring persistence. And while you are still in that headspace, you can linger on one more quiet detail. The crater was not discovered once. It was discovered repeatedly by different people with different slices of the evidence. Anomalies noticed, then forgotten, then noticed again, then reframed. In science, that happens more than we like to admit, because knowledge is not just data, it is context. A gravity anomaly is meaningless until you have a reason to interpret it as a crater. A breccia in a drill core is just an inconvenience until you understand impacts. And a thin clay layer with iridium is just a curiosity until you connect it to an extraterrestrial source. So the Chicxulub story is less like a single discovery and more like a slow synchronization of clocks. Different fields, ticking at different speeds, eventually align. Now you are ready to drift into the next part of the journey, where the crater stops being a local structure and becomes part of a global narrative. But before you get there, you stay with the calm mechanics of confirmation, because this is where the story is most human. Picture a core lab, fluorescent lights, a long table, rows of core boxes opened like drawers. The rock is damp. It smells faintly mineral, like wet concrete. Someone is writing on a clipboard, because science is 90% writing things down so you can argue later. The routine is simple. Describe the lithology, meaning the rock type. Note the grain size, note the color, mark the contacts where one layer ends and another begins. Sometimes you scratch the rock with a tool to see how it behaves. Sometimes you drip acid on it, because limestone fizzes when it meets weak acid. That fizz is carbon dioxide being released, a tiny chemical sigh from ancient shells. And then, deeper in the core, the fizz changes, the texture changes, the story changes. You start to see fragments that do not belong together. Pieces of different rocks in one layer, clasts that are too angular to have been rolled by water for long. Angular fragments suggest minimal transport. They suggest violent breakage nearby. And when you see melt fragments dark and glassy, you start to suspect you are no longer in normal sedimentary time. You are in aftermath. You can also measure physical properties. Density, magnetic susceptibility, meaning how a rock responds to a magnetic field. Porosity, how much empty space is inside it. Impact rocks can have distinctive values because they have been fractured, melted, and altered. If you are especially patient, you can look for tiny spherules. These are little beads of glass, formed when molten material is thrown into the air and cools into droplets. They can be preserved in certain deposits, sometimes altered into clay minerals over time. Finding them is like finding microscopic hailstones from a storm that happened 66 million years ago. And then there is geochemistry. You can analyze the composition of these rocks. Look for enrichment in elements like iridium, osmium, nickel, things that can be associated with meteorites. You can look at isotopes too, subtle variations that can indicate extraterrestrial input. All of this is slow work. Samples are cut, powdered, dissolved, run through instruments. The results come back as numbers, which is always a little funny because you are trying to describe an ancient planetary catastrophe in the language of spreadsheets. But the numbers, if they are consistent, give you confidence. And confidence is what lets you connect the crater to that thin boundary layer found around the world. The boundary itself has a name that sounds like a password: the KPG boundary. It marks the transition between the Cretaceous period and the Paleogene period, between the world with non-avian dinosaurs and the world after. In rock outcrops, it can be a thin clay layer, sometimes just a centimeter or two. A small pause, it is the geological equivalent of a quiet line break. And inside that clay, scientists found an enrichment in iridium. Iridium is rare in the Earth's crust because most of it sank into the core during differentiation when the planet was young and molten. But meteorites, especially certain types, can have more iridium relative to crustal rocks. So an iridium spike suggests an influx of extraterrestrial material. The idea was championed famously by Luis Alvarez and his colleagues, including his son Walter Alvarez, in the late 1970s and early 1980s. They proposed that an asteroid impact could explain the iridium anomaly and the mass extinction. At first, not everyone was pleased with this idea. Geologists and paleontologists had other explanations: volcanism, sea level changes, climate shifts. And to be fair, the Earth was doing multiple things at once. It rarely limits itself to one crisis at a time. But the impact hypothesis had a special appeal. It explained the global distribution of the anomaly, and it offered a mechanism for sudden change. Still, a hypothesis needs a crater. You cannot accuse a planet of being hit without showing where it was hit. So for a while, the impact idea floated with a missing centerpiece. People searched for craters of the right age. They found candidates. They argued, and in the background, the ring under the Yucatán waited like an unclaimed confession. When Chicxulub became widely recognized as the crater linked to the boundary, it was not just because it was big. It was because the timing matched. The location matched ejecta patterns. The geology matched impact signatures. And it fit into the growing web of evidence, like the final piece of a puzzle that had been left under the couch. But you are still not obligated to get excited. You can keep it calm. Because even a global catastrophe, when you view it through rocks, becomes a matter of textures and thin layers. You can hold the boundary in your hand. A smear of clay, a subtle color change. It is strangely small for something that marks such a profound transition. And that is one of geology's best bedtime lessons. The biggest events can leave the thinnest traces. So now, gently, you pivot from crater formation and discovery into what those traces actually mean. Not in a cinematic way, in a slow, physical way. Imagine dust. Not a dramatic cloud you can see from space, just fine particles suspended in air, making the sunlight look tired. A large impact throws material high into the atmosphere. Some of it falls back locally as ejecta. Some of it spreads globally. Fine dust and aerosols can stay aloft, reflecting sunlight, cooling the surface. You do not need to picture darkness. Just picture dimmer days. Plants rely on sunlight. Phytoplankton rely on sunlight. Food webs start with photosynthesis. So if you interrupt sunlight for long enough, ecosystems feel it. Then there are sulfur aerosols. If the impact vaporizes sulfate-rich rocks, it can inject sulfur dioxide into the atmosphere. Sulfur dioxide can form sulfate aerosols, which also reflect sunlight and can contribute to cooling. It can also lead to acid rain, which is not soothing, but it is part of the chemical aftermath. Again, you do not need to dwell on suffering. Just notice the chain. Impact hits certain rocks. Certain gases are released. Atmosphere changes. Climate responds. Life, which is always precarious, adapts or fails. And in the sediments, you see the signature. A boundary clay, soot in some places, shocked minerals, spherules. In ocean sediments, you can see changes in microfossils. Species disappear. Others become common. It is a reshuffling. The world does not end. It changes employees. Now, while you are holding that thought, you can appreciate something else. Chicxulub is not the only scar on Earth. It is just the most famous in this context because it is tied to an extinction boundary that humans find narratively satisfying. But the Earth has been hit many times. Most craters are older, smaller, more eroded or hidden under oceans and sediments. Some are visible as circular lakes. Some are rings of hills. Some are only found through gravity anomalies and drill cores, just like Chicxulub. And the reason there are not more obvious craters is that Earth is efficient at erasing. On the Moon, craters last because there is no weather, no flowing water, no plate tectonics recycling crust. On Earth, the surface is temporary. Rocks are lifted, eroded, buried, melted, and reused. The planet treats its own crust like a rough draft, so an impact scar has to fight for visibility. This is why Chicxulub is such an oddity. Not because it happened. Impacts happen because it is preserved well enough, and recent enough, and studied enough to be understood in detail. And now your mind can start drifting outward from this one crater to the wider habit of the planet. But you do it slowly. You stay with the idea that geology often works backward from subtle clues. A thin layer of clay, a faint ring in gravity data, a few shocked grains under a microscope, and from these, you reconstruct an event that lasted seconds. Seconds. That is the part that never stops being slightly absurd. The impact itself was over almost immediately. The shock wave raced through the crust. The crater formed. Material fell back, and then the planet returned to its slow routines. Sediments settled. Water circulated. Life continued, changed, adapted. And 66 million years later, you lie in bed listening to someone like me talk about it in a calm voice, as if it is a bedtime story, which, in a way, it is. Because geology is not the story of violence. It is the story of after. And speaking of after, there is a particular kind of after that geologists love because it is measurable and quietly revealing. The way the crater is filled. When a crater forms, it is a depression. Over time, it becomes a basin for sediments. In marine settings, the first deposits can include chaotic debris flows, slumps, and reworked material. Imagine underwater landslides triggered by the impact and the shaking. Sediment and debris rushing into the crater, filling it unevenly. Then, as conditions stabilize, finer sediments settle, calm returns in layers. So in a core, you might see a transition, chaotic breccias, then graded beds, then more normal limestone, or marl. Marl is a mix of carbonate and clay. It forms in quieter marine environments. These transitions help reconstruct the sequence of events after the impact, not minute by minute, but phase by phase. And in some places, you can even identify deposits interpreted as tsunami-related. A large impact in shallow water can generate massive waves. Those waves can scour coastlines and deposit unusual layers. In the geological record, tsunami deposits can be tricky because storms also make high-energy layers, but impacts can generate deposits that are unusually widespread, thick, and associated with ejecta material. So again, you do not rely on one clue. You rely on a cluster. A high-energy deposit plus spherules plus shock minerals plus the right age. Geology is always building cases, not making declarations. Now, you let that settle, and you drift toward the next stretch of the story. Because once the crater is outlined and confirmed, your mind naturally wanders to the broader question of why it matters and how it fits into Earth's habit of both sudden change and slow change. And the calm truth is that Chicxulub is a doorway into both. It is sudden violence recorded in shock features. It is slow burial recorded in limestone blankets. It is global consequence recorded in a thin clay line around the world. It is also a reminder that the ground under ordinary places can hold structures bigger than your entire sense of scale. A sleepy town name, Chicxulub, attached to a crater wider than the distance you could drive in a day. And while you are thinking about that mismatch between everyday life and deep structure, it becomes easier to accept a larger theme. The Earth is full of hidden geometry, not just craters. Salt domes, buried reefs, ancient river channels filled with different sediments, fault zones sealed and reopened, basins subsiding, uplifts rising. Most of it is invisible from the surface, which is why geologists learn to see with proxies, gravity, magnetism, seismic waves, drill cores. They learn to listen to the planet indirectly. And because you are here for a bedtime story, you get to enjoy the indirectness without the paperwork. You get the ghost of the discovery, not the meetings. So you keep moving gently through the logic. A crater is identified. Its impact fingerprints are found. Its burial is understood. Its timing is linked to a boundary. And then your attention drifts like a flashlight beam to the boundary itself, far from the crater. Because the strangest part of this story is that you can stand on cliffs in Italy or Denmark or the Western United States and find that same thin line, a global layer, marking a moment. This is the part where the Earth feels almost coordinated, like it wanted to leave a bookmark. But the coordination is just physics. Dust and aerosols spread, ejecta falls, particles settle. A global rain of fine material, thin enough to be overlooked, thick enough to be detected. And the scientists who first studied it often were not looking for an impact either. They were doing stratigraphy, the study of rock layers. Stratigraphy is the art of noticing subtle changes, a shift in fossil species, a change in sediment composition, a thin clay seam. It is slow, careful work, the kind of work that rewards people who do not need fireworks. So, when the iridium anomaly was found, it was a clue that something unusual happened at that boundary. And when shocked quartz was later found in boundary sediments, It strengthened the impact case. Shocked quartz is difficult to produce in normal Earth conditions. Volcanic eruptions, even huge ones, do not usually generate the same planar deformation features. So finding shocked quartz in the boundary layer was like finding a specific tool mark at a crime scene. Then there were spherules. In some boundary deposits, scientists found tiny glassy spheres, altered over time but still recognizable. They represent molten droplets ejected and cooled, and their composition can sometimes be matched to target rocks, meaning you can analyze them and infer what kind of crust was vaporized. When that composition matches carbonate and sulfate-rich targets, it points toward an impact in a place like the Yucatan. Again, convergence. Now, you might wonder why you do not find a thick layer of impact debris everywhere. Because most of the ejecta is fine. Much of it becomes mixed with normal sediments. And erosion removes some records. The boundary is preserved best in certain quiet depositional environments, like deep sea sediments that accumulate slowly and evenly. In those settings, a thin, unusual layer stands out. On land, records can be patchy. Rivers erode, soils form, sediments get reworked, so the boundary can be missing in many places or altered. This is why geologists treasure the places where it is clear. They are like intact pages in a book with many torn chapters. And once you accept that, you are ready to drift toward other hidden scars, because Chicxulub is the gateway drug. Once you learn that a crater can hide under a calm limestone platform, you start suspecting everything. A circular lake in Canada, a ring of hills in South Africa, a subtle gravity anomaly under a wheat field. The Earth is not smooth. It is simply well covered. So you let your imagination move slowly away from the Yucatan. You picture older craters that have been softened by time. One classic example is the Vredefort structure in South Africa. It is one of the largest and oldest known impact structures on Earth. So old that the original crater shape is mostly gone. What remains is a complex pattern of deformed rocks, a dome-like uplift, and ring-like geological structures. If you stood there without context, you might see hills and ridges and think, tectonics did this. And you would not be entirely wrong, because over billions of years, tectonics and erosion have overprinted everything. But the impact signature is still there in the rocks, in shock metamorphism, in shatter cones. Shatter cones are another impact fingerprint. They are conical fracture patterns in rock, with striations that radiate outward. They look a bit like someone tried to sculpt the rock into a stack of nested cones. They form under shock conditions, and they can be found at some impact sites. If you ever hold one, it feels like the rock is pointing back at the impact center, like a compass made of trauma. Another example is the Sudbury Basin in Canada. It is a large impact structure that is also economically important because it hosts rich ore deposits, nickel, copper, platinum group elements. The impact melted and rearranged crust, creating conditions that concentrated metals. So yes, sometimes planetary violence creates mining opportunities. Congratulations, your apocalypse is someone else's retirement plan. Sudbury is also heavily altered and deformed, but its impact origin is widely accepted based on geological and geochemical evidence. Then there is the Clearwater Lakes in Canada, which are two lakes occupying impact craters. From above, They look like neat circles, like someone pressed a finger into the landscape. Those are the ones people like to photograph because they are visually satisfying. But many craters are not so neat. Some are buried under sediments, like Chicxulub. Some are offshore. Some are fragmented by faulting. Some are eroded into shapes that no longer look circular. So discovery methods vary. Sometimes it starts with satellite imagery, noticing a circular feature. Sometimes it starts with field mapping, finding breccias and shocked minerals. Sometimes it starts with geophysics, mapping anomalies. Sometimes it starts with drilling for entirely different reasons. And then, as with Chicxulub, someone connects the clues. Now, speaking of connecting clues, there is a quiet pattern that links many crater discoveries. They often require a shift in mindset. You have to be willing to ask if an ordinary geological feature could be extraordinary. A circular lake might be glacial, or it might be impact. A breccia might be volcanic, or it might be impact. A gravity anomaly might be salt, or it might be impact. So you learn to look for discriminators. Shock metamorphism is one. Extraterrestrial geochemical signatures are another. Crater morphology, where preserved, is another. And sometimes you get lucky and find multiple discriminators in one place. But luck is rarely enough. You need persistence, because impacts are brief and the Earth is always busy afterward. That is why, even though impacts have happened throughout Earth history, the confirmed crater record is incomplete. Most impacts happened in the ocean because most of Earth is ocean. Ocean crust is recycled on timescales of hundreds of millions of years. Subduction zones swallow it. New crust forms at mid-ocean ridges, so the ocean floor does not preserve very old craters. The continents do better, but they too are eroded and altered. So the preserved crater record is biased toward younger and more recent impacts and toward craters in stable continental interiors. Chicxulub is a special case because it is relatively young and it was buried rather than eroded away, and it sits on a stable platform. It was hidden, but preserved, and that is why it could be found. Now, you can let this broader crater context sit in your mind like a quiet background hum, because it prepares you for the next pivot. Impacts are sudden, but they are not the only way the Earth rearranges itself. There is a slower machinery that sets the stage for everything: plate tectonics. And it is hard to overstate how slow plate tectonics feels, especially compared to an impact. Continents move at about the rate your fingernails grow. You do not notice it day to day. But given millions of years, coastlines migrate, oceans open, mountains rise, and basins form. The Yucatán platform itself exists where it does. Because of that slow dance, it is part of the North American plate, a stable carbonate platform built over time, influenced by ancient ocean basins and shallow seas. To understand why the crater is buried under limestone, you need to understand why there was limestone there to begin with. Limestone forms in warm, shallow, clear seas where carbonate-producing organisms thrive. Corals, algae, shell-forming creatures. They create calcium carbonate skeletons and shells. Those accumulate when conditions are right. The Yucatan region has spent long intervals submerged under shallow tropical waters, making it a factory for carbonate sediments. So, while the impact was a sudden, violent punctuation, the broader chapter was written by slow sedimentation and plate-driven geography. seas advance and retreat with changes in sea level, which can be driven by tectonics and climate. During times of high sea level, shallow seas flood continental margins, creating broad platforms where carbonates accumulate. During low sea level, those platforms can be exposed and eroded, then flooded again. This cycling creates layers. So you can imagine the Yucatan as a patient builder, laying down one pale layer after another, long before the asteroid arrived and long after it left. And the crater, when it formed, became just another low spot in that building project, filled, covered, forgotten, until humans came along with instruments. Now, you let that be the bridge, because you are shifting from sudden impacts to slow processes, from a single ring to the whole planet's slow choreography. But before you fully leave the crater behind, you keep one last detail in your pocket. Even when a crater is buried, it can influence the landscape subtly. The fractured rocks can affect groundwater flow. The circular structure can guide dissolution patterns in limestone. The crater can become a ring of slightly different permeability. So sometimes, surface features like arcs of cenotes might reflect deeper structure, not as a direct crater rim you can hike, but as a tendency. Water finds pathways, fractures provide pathways, and impacts create fractures, so the crater can whisper into the hydrology of the region. It is a quiet afterlife. And now, with that quiet afterlife in mind, you drift fully into the long, slow motions. The Earth's surface is divided into plates: oceanic plates, dense and thin; continental plates, thicker and buoyant. They move because the mantle beneath them convects slowly circulating heat from Earth's interior to the surface. Convection in the mantle is not like boiling water you can see. It is rock, solid rock, deforming over millions of years. The mantle behaves like a very stiff fluid on long timescales. Heat makes it less dense. It rises, it cools, it sinks. This circulation drags plates. At mid-ocean ridges, plates diverge and new ocean crust forms. At subduction zones, ocean crust sinks back into the mantle. Continents collide and crumple into mountain ranges. They split apart and form new ocean basins. And through all of this, sediments accumulate in basins and on shelves. So when you look at a flat carbonate platform like the Yucatan, you are seeing a relatively stable part of a plate, a region that has avoided being crumpled into mountains for a long time. Stability is what allows thick sedimentary sequences to build. If the region were being uplifted and eroded constantly, the layers would be stripped away. Instead, the Yucatan stayed low, often submerged, allowing carbonates to pile up. That is why the surface is smooth. That is why the crater could be buried, and if you zoom out further, you can see that the Gulf of Mexico itself has a tectonic history. It opened during the breakup of the supercontinent Pangaea as North America separated from other landmasses. Rifting created a basin. Seafloor spreading created oceanic crust in the deep Gulf. Over time, sediments filled parts of the basin and carbonate platforms developed along the margins. Salt was deposited in the basin early on, during restricted marine conditions. That salt later played a role in Gulf geology, forming domes and influencing sediment structure. So when geophysicists first saw circular anomalies in the Yucatan, they had to consider salt tectonics as an alternative explanation. Salt can flow under pressure, rising and deforming overlying layers. It is buoyant relative to many sediments. It moves like slow toothpaste. Salt structures can create domes, faults, and ring-like features. So in the Gulf region, salt is always a suspect, which makes impact confirmation even more dependent on shock features. Now, you can let plate tectonics and sedimentation become the new baseline rhythm. Slow movement, slow accumulation, slow burial. And you can see how sudden events like impacts are layered into a world that is otherwise patient. The planet is both impulsive and methodical. It can throw an asteroid at you and then spend millions of years quietly covering it up. And while you hold that duality, your mind is ready to slip into something even gentler. Layers. Because once you accept that the Earth writes in layers, you can start reading them like pages, not just for impacts, but for everything. Storms, sea level changes, climate shifts, biological evolution, all recorded in stripes of rock. And the comforting part is that most of those stripes are not dramatic. They are quiet differences in texture. A little more clay here, a little more carbonate there, a slightly different fossil assemblage. In a core, layers can look like subtle color changes. Pale gray to slightly less pale gray, the geological equivalent of different shades of beige paint. But those small differences can tell you about ancient environments. A sandy layer might mean a higher energy shore, waves and currents. A muddy layer might mean deeper, quieter water. A carbonate-rich layer might mean clear, warm seas with abundant life. A layer with evaporite minerals might mean restricted basins, hot climates, evaporation. So when geologists read layers, they are reconstructing ancient landscapes without ever seeing them. It is a kind of time travel that smells like wet rock and paperwork. And it is especially satisfying because it is slow. You do not need to rush. The planet took millions of years to write these pages. You can take a few minutes to read them. So you imagine yourself holding a slab of sedimentary rock. It has bedding planes, flat surfaces where layers split. You run your finger along the boundary between layers, and you can feel a tiny step, a change in grain size. That boundary might represent a storm, or a season, or a longer shift in conditions. In some rocks you can see laminations, very thin layers, like pages in a tightly bound book. In lake sediments, you can get varves, annual layers, one light and one dark, recording seasonal changes. In marine settings, layers can record longer cycles, driven by climate and sea level. And then, occasionally, you get an interruption. A layer that does not fit, a volcanic ash layer, fine and widespread, deposited quickly. A tsunami deposit, chaotic and coarse. An impact ejecta layer with spherules and shocked minerals. These interruptions are the punctuation marks. The rest is mostly quiet prose. And this is why Chicxulub matters to geology beyond dinosaurs. It is a marker layer event, a time horizon that can be recognized globally. If you find the KPG boundary, you can correlate rocks across continents. You can align timelines. A thin layer becomes a global synchronizing point. It is like a timestamp written in clay. So you can see why stratigraphers care, why paleontologists care, why geophysicists care. It is a rare moment when multiple disciplines can point to the same thin line and agree something happened here. Agreement is rare in science, so when it happens, it is worth noting quietly. Now, with layers as your new focus, you can begin to drift into the next stretch of the story, where you read sediments not just as records of catastrophe, but as records of ordinary time. Because ordinary time is what dominates the rock record, and ordinary time in geology is still strange. Ordinary time includes coastlines moving miles. It includes seas appearing over continents. It includes mountain ranges rising and eroding into plains. It includes creatures evolving, diversifying, going extinct, leaving fossils that become part of the layers. So, as you transition into that calmer view, you keep Chicxulub as one example of how a thin, odd layer can lead you to a buried structure. A detective story told in mud and limestone. And you begin, slowly, to treat every layer like a clue. Not an urgent clue, a quiet clue. One that will still be there in the morning, and the morning after that, and the morning after that, because rocks are patient like that. And speaking of patience, there is nothing more patient than sediment itself. Sediment is just the planet's leftover material, moved by water and wind, sorted by gravity, and laid down wherever energy drops. A grain of sand does not want anything. It just rolls until it cannot. A clay particle is so small, it stays suspended for a long time, drifting until still water lets it settle. Carbonate mud forms from tiny bits of shells and chemical precipitation. So when you look at a sedimentary basin, you are looking at a place where the planet has been slowly exhaling its worn-down surfaces. Mountains erode, grains travel, basins fill. And if you get sleepy thinking about that, good, because this is the slow heartbeat behind the whole story. Even Chicxulub, for all its sudden violence, was eventually turned into sediment and covered by sediment. The planet ate the evidence and filed it in layers. Now you are ready to sink deeper into the comfort of stratigraphy, where the world becomes a stack of calm observations. And you start with the simplest idea. Older layers tend to be below younger layers. It sounds obvious. It is not always true, because folding and faulting can flip layers. But in many undisturbed sedimentary sequences, it holds. So depth is a kind of rough time. And when you pull up a core, you are pulling up time in order. You can move your finger from top to bottom and travel from younger to older. The Chicxulub core sections, the ones that cross the impact-related layers, are especially dramatic in the middle. But above and below, there is a lot of normal limestone. And that normal limestone matters, because it tells you what the world was like before and after. Before, carbonate platform, warm seas. After, carbonate platform again, eventually. Which is the quietest kind of resilience. Not heroic, not moral. Just environmental conditions returning, organisms returning, sedimentation resuming. The earth does not mourn. It resets. So as you move into reading layers like bedtime pages, you carry that tone with you. Not despair, not triumph, just process. Layers forming, one on top of another, while the planet turns. And as you trace those layers in your mind, you start noticing how the story becomes less about any single event and more about the steady, in different active recording. The planet records everything, whether you like it or not, but it records it in a language that is easy to miss, a slightly different texture, a thin clay seam, a subtle anomaly in gravity. So you keep listening for the soft differences. Because in geology, a difference does not have to be loud to be real. You are looking at a bed of limestone that seems identical to the one above it, but it breaks differently. The fracture is cleaner, the grains are finer, the surface feels slightly waxy. That tiny change can mean the water was deeper or calmer or simply clearer. It is almost insulting, honestly. You expect the planet to annotate its own history with something polite and readable. Instead, it gives you shade variations, and you are supposed to reconstruct oceans from beige. But this is how stratigraphy works when it is behaving itself. You let the rock talk in its smallest voice. A layer that is a little more clay-rich can tell you the sea carried more dust. Maybe a distant coastline eroded faster, feeding rivers with mud. Maybe winds were stronger, and the air delivered fine particles across open water. A layer that is a little more chalky can mean more microscopic life in the sea. Tiny plankton making tiny shells, dying and settling slowly. When those shells build up, the rock turns pale and soft-looking. And then you hit a contact that is sharper than it should be, a boundary that looks like someone drew a line and stopped. That can mean a sudden change, a storm, a flood, a rapid sea level shift, or sometimes it means time went missing. Geologists have a word for missing time, an unconformity. It sounds dramatic, but it can be very subtle. An unconformity is just a surface where deposition paused or erosion removed layers. In human terms, it is a torn page. The story jumps, and the rock pretends it did not. You can stand in front of a cliff and see it. Beds below tilted, beds above flat, with a hard boundary between. That is the famous cinematic version. But in places like carbonate platforms, it can be sneaky. Limestone dissolves easily in slightly acidic water, so you can lose time without losing obvious thickness. A pause in sea level exposes the platform. Rainwater moves through soil, picks up carbon dioxide, becomes weak acid. It seeps into cracks, and the limestone fizzing happens underground. So while you are above, living your brief little human life, the platform is being quietly edited. Caves enlarge, fractures widen, surfaces become irregular. Then sea level rises again, and new sediment drapes over the dissolved surface. The result is an unconformity that is not a dramatic cliff face. It is a subtle change in texture, a hard ground, a thin crust where the sea floor cemented. Sometimes it is stained or bored by organisms or studded with little mineral nodules. You would miss it if you were rushing. And that is why the Chicxulub story fits so well into this broader habit of reading layers. Because even with a crater underneath, the surface record is mostly quiet carbonate time. Warm seas, shell snow, gentle chemistry. Then, hidden in the stack, there is a layer that refuses to be normal. Not because it is thick, because it is strange. When scientists describe the boundary layer in different locations, they often mention things that sound small. A spike in iridium, a scattering of shocked quartz grains, a little soot, tiny spherules altered into clay. It is the kind of evidence that could fit in a spoon, and it marks a planetary event. This mismatch between scale and trace is one of the most calming truths in Earth science. It means the world can change violently and still leave a signature that is polite. A thin seam, a whisper of chemistry. Now, you let that whisper lead you into other hidden scars, because Chicxulub is not lonely. Think about how many impacts should have happened. The solar system formed messy. Leftovers kept orbiting. Earth has been sweeping its neighborhood for billions of years. But your planet is also a compulsive recycler. On the moon, a crater sits where it formed, like a bruise that never fades. No rain, no rivers, no soil-burrowing organisms, no plate tectonics dragging crust back into the mantle. On Earth, even mountains are temporary. Water dismantles them grain by grain, and basins swallow the debris. So most craters are either erased or disguised. Sometimes you find them because the landscape still holds the shape. A circular lake with a raised rim of hills, a ring of islands, a gentle bowl that does not match the surrounding terrain. Those are the friendly ones. Other times, you find them because the rocks are wrong. Shocked minerals, melt rocks that look nothing like nearby volcanics, breccias with the chaotic energy of a place that was instantly remodeled. And sometimes you find them because the planet feels different beneath your feet. Gravity anomalies, like a hidden weight. Magnetic anomalies, like a rewound tape. A famous example is that older, battered structure in South Africa, Vredefort. It is so ancient that the original crater is gone as a simple shape. What remains is a distorted core of uplifted rock, surrounded by rings of deformed geology. If you are standing there, you are not admiring a bowl. You are walking through a place that was squeezed, shocked, and then rewritten by a couple billion years of tectonics. It is an impact scar that learned how to wear a different face. Another is Sudbury in Canada. Also ancient, also deeply altered, but economically irresistible. The impact there created a large melt sheet, a pool of hot rock that cooled and differentiated. In simple terms, heavier materials sank, lighter materials rose, and certain metals concentrated. Nickel and copper, and those platinum group elements that humans love to chase. Because if you are going to be a species with anxiety, you may as well turn trauma into jewelry. Sudbury became a mining district, and its impact origin was argued over for years. It took shock features, melt geology, and geochemistry to make the case stick. And those debates are part of the charm if you are the kind of person who finds comfort in slow arguments. Because an impact crater is not always obvious even when it is huge. Earth has too many ways to create circular patterns. Volcanoes can collapse into calderas. Salt can rise into domes. Tectonics can bend layers into arcs. So when someone proposes impact, the next question is always, show me the shock. Shocked quartz is the classic, but there are others. Shatter cones, those conical fracture patterns, are another signature. They can form in the bedrock beneath an impact, where shock waves refract and focus. If you find shatter cones, you are basically holding a fossilized pressure wave. It is rock that got punched so hard it grew a pattern. There are also high-pressure minerals like coastline and stishovite. They are silica, but compressed into structures that normally require extreme pressures. In human terms, the crystal lattice got rearranged under duress. Same chemical recipe, different architecture. Finding those minerals is like finding a building made of the same bricks, but stacked in a way you only see after a disaster. And then there are geochemical fingerprints. Impactors can bring in elements like iridium, and sometimes their isotopic ratios can stand out. Sometimes you can even find tiny remnants of the impactor itself, metallic grains or spinels, microscopic minerals that survived stubbornly. Not always. Often the impactor is vaporized and mixed into the melt and ejecta, but occasionally the record keeps a few crumbs. So the Earth is a scrapbook, but it is not organized. Pages overlap, glue stains appear, some photos are missing, and every so often you find a circular tear in the paper. Now, there is a darker little fact that keeps all of this from becoming too sentimental. Most impacts happen in the ocean. You do not notice because you were not around for most of them, and because the ocean is good at hiding evidence. Deep ocean crust is young in geological terms. It is made at mid-ocean ridges and destroyed at subduction zones. The average age is not ancient compared to continents. So if an impact crater forms on oceanic crust, it has a deadline. Eventually, it is dragged down, heated, metamorphosed, and erased into mantle memory. That means the crater record you know is incomplete, biased toward continents, toward stable interiors, toward places that avoided being recycled. Chicxulub is preserved partly because it is on a continental platform, and partly because it was buried, not stripped away. Burial is a form of protection. Erosion is more chaotic, which brings you to a strange comfort. The ground beneath you is not permanent, but it is patient. It will keep what it can, and it will erase what it must. Now, while you are thinking about scars and recycling, you drift naturally back into slow motion plate tectonics again. Because even impacts, for all their drama, are imposed on a planet whose main habit is gradual rearrangement. The continents you know have not always been where they are. They wander, millimeter by millimeter, across the mantle. Ocean basins open, widen, then close. Mountain ranges rise, erode, and disappear. Coastlines shift as sea level rises and falls. And your calm, flat Yucatán platform is not a random location. It is a product of that long rearrangement. The Gulf of Mexico formed during the breakup of Pangaea. Rifting stretched the crust, thinning it, letting the basin subside. Seawater entered. Salt was deposited during restricted conditions, when evaporation outpaced inflow. Later, as the basin matured, sediments poured in from surrounding highlands. Rivers delivered sand and mud. Carbonates formed on the shelves in warmer, shallower regions. Over time, thick stacks built up, one layer at a time. In that setting, a carbonate platform is like a quiet factory. It produces limestone steadily, but only when conditions stay gentle. Warm water, shallow depths, clear enough for carbonate-producing organisms. Low input of mud, because too much mud smothers carbonate production. So when the platform is healthy, it builds pale rock like a slow snowfall. If sea level changes, the platform responds. Expose it, and you get dissolution. And caves, flood it, and you get more carbonate sediment. That cycle is one reason the Yucatan has so much karst. Repeated exposure and flooding makes limestone vulnerable to water's slow appetite, and that is why the surface is such a liar. It looks simple, but underneath it is riddled with voids, fractures, and hidden flow paths. Now, take that idea of slow plate-driven change and connect it back to crater discovery. Because one of the quiet tricks in this story is that industry data became scientific treasure. Oil exploration produced seismic lines. Those lines were designed to find petroleum traps. But the same sound waves can reveal crater rings. Gravity surveys were meant to map structures, but the density contrasts of a crater show up too. Magnetic surveys were meant to detect changes in basement rock, but impact-altered magnetism leaves patterns. So, the Earth gave up its secret not because someone demanded it, but because humans kept measuring things for practical reasons. And this is where you can appreciate, calmly, how confirmation works in science when nobody is allowed to rerun the event. You want multiple independent measurements. A gravity anomaly alone is suggestive. A circular magnetic anomaly strengthens it. Seismic profiles showing a peak ring strengthen it again. Then you drill, because drilling is the only way to touch the rock and ask it directly. Cores give you lithology. Thin sections give you microstructures. Geochemistry gives you composition. When all of those agree, you stop calling it a hypothesis and start calling it a structure. This process is not glamorous. It is slow convergence, like fog condensing on glass. And once you understand that, the Chicxulub discovery stops being a single moment. It becomes a long, distributed act of noticing. Now, your attention can return to sediments again, because there is another gentle skill geologists use: correlation. Correlation is matching layers from one place to another. It is how you build a timeline across distances. If you find the same volcanic ash layer in two different regions, you can line them up. Ash can be dated because volcanic minerals often contain isotopes that decay at known rates. If you find a distinctive fossil assemblage, you can correlate biostratigraphically. Certain microfossils appear and disappear in the record, and their presence can indicate a particular interval. If you find the KPG boundary layer with its iridium and shocked minerals, you can correlate that too. But correlation always comes with caution, because two layers can look similar and still be different ages. That is why geologists love multiple markers. Fossils plus chemistry plus ash layers. Not just one clue. In carbonate sequences, correlation can be tricky. Limestone can look monotonously similar over long intervals. So you use subtle variations, isotope ratios in carbon and oxygen, changes in fossil species, tiny shifts in clay content. Carbon isotopes can reflect changes in the global carbon cycle. Oxygen isotopes can reflect temperature and ice volume. In broad terms, when interpreted carefully, those isotopes are like mood rings for ancient oceans, except less honest and more mathematical. You sample a sequence, measure isotope ratios, and look for patterns. A shift can suggest a climate change, or an ocean circulation change, or a productivity shift. And in the aftermath of Chicxulub, there are changes in the carbon cycle recorded in sediments. A disruption, then a recovery. But recovery is not instant. It is layered. That is another calming part of the story. Even after a sudden event, the return to equilibrium takes time. You can see it in microfossils. In marine sediments, plankton species shift. Some groups decline sharply at the boundary, others persist, and then diversify later. It is not a clean reset button. It is more like reorganizing a crowded room after someone knocked the shelves over. Now, since your mind is already in the sediment diary, you can zoom into one of the most comforting tools in stratigraphy: grain size. Grain size is almost childishly simple, and it tells you a lot. Coarse grains like sand settle quickly and require higher energy water to move. Fine grains like clay settle slowly and can travel far in suspension. So a sandy layer might mean a stronger current, a storm, a near-shore environment. A clay layer might mean quieter water, deeper settings, or simply less energy. In some cases, you see graded bedding. Coarse at the bottom, fine at the top. That can indicate a turbidity current, an underwater avalanche of sediment. Those flows happen when sediment on a slope becomes unstable and rushes downslope. They can be triggered by earthquakes, storms, or rapid sediment loading. After a large impact, you can trigger slope failures. Shaking destabilizes sediments. Waves and currents rework material. So, within crater basins and on nearby slopes, you might see deposits that suggest rapid, energetic transport. But again, you stay calm about it. It is just sediment obeying gravity. Sediment does not panic. It slides. Now, there is a subtlety here that matters to the Chicxulub story. People sometimes imagine the boundary layer as a single uniform deposit. In reality, it varies a lot by location. Close to the crater, you can get thick, chaotic deposits, ejecta blankets, breccias, reworked material, tsunami deposits, impact melt. Farther away, you get thinner layers. Just a dusting of spherules, a thin clay seam enriched in iridium, a few shocked grains. In deep ocean settings, you might get a very clean boundary clay because sedimentation was slow, so a sudden influx stands out sharply. In nearshore or terrestrial settings, erosion and reworking can smear the record. The boundary can be hard to find or missing. So the best preserved global markers often come from quiet places, deep sea sediments where accumulation is steady and disturbance is minimal, which is a lovely, sardonic lesson. The biggest events are recorded best where nothing usually happens. Now, let your mind drift back toward Chicxulub one more time, but in a different mood. Not as the Extinction crater, as a heat engine. After the impact, the crater contained hot melt, fractured rock, and circulating water. That hydrothermal system is not just a curiosity. It can alter minerals in ways that persist. It can deposit veins. It can create zones of clay alteration and chemical changes. When scientists drilled into the peak ring, they found evidence that the rocks were heavily fractured and altered. There were minerals that suggested hot water moved through the system. This matters because it tells you impacts have long afterlives. The crater is not dead after the dust settles. It is chemically active for a while, and for microbial life, hydrothermal systems can be attractive. Heat plus water plus chemical gradients. So impacts are not only destructive, they can create temporary environments that might support life. If that feels like the universe trying to apologize, do not fall for it. It is not kindness. It is chemistry. Now zoom out again. The same principle applies elsewhere. Impact craters can host lakes. Lakes accumulate sediments. Those sediments can preserve fine-scale records of climate and ecology. So a crater can become an archive, not just a scar. Some crater lakes preserve laminated sediments, seasonal layers, that record environmental changes over thousands of years. You get pollen grains. You get dust records. You get chemical signals. A crater turns catastrophe into a filing cabinet. That is Earth's general move. Now, while the planet is filing things away, plate tectonics keeps moving the shelves. Subduction zones swallow ocean crust. Collisions raise mountains. Rifts open new basins. And all of that tectonic motion sets the stage for where sediments accumulate and where layers are preserved. Basins are preservation machines. They subside, creating space for sediment to fill. If you want a long, continuous record, you look for a basin that stayed subsiding gently. If you want missing time, you look for uplifted areas that were eroded. The Yucatan is a platform, not a deep basin, but it is stable enough to preserve thick carbonate sequences. It stayed close to sea level, repeatedly flooded, repeatedly building limestone. And that stability is why Chicxulub is buried, not displayed. Now, if you keep following this slow, layered logic, you end up with a kind of bedtime truth. Geology is not just about events. It is about rates. Fast processes leave sharp boundaries. Slow processes leave thick accumulations. But even slow processes can leave sharp boundaries if conditions shift quickly. Sea level changes can be relatively rapid. Climate changes can shift sediment supply. Volcanic ash can fall in days. So the rock record is a mixture of slow background and sudden punctuation. A quiet book with occasional torn pages and coffee stains. Now, speaking of quiet books, there is another detail that helps you read sediments like pages. Sedimentary structures, ripple marks, for example. Little ridges formed by moving water or wind. If you find ripples preserved in sandstone, you can infer flow direction. You can tell which way the current moved long after the water is gone. Cross-bedding, those angled layers within a bed, can indicate dunes migrating in a river. Or in a desert, mud cracks can indicate exposure to air, drying, and shrinking. Bioturbation, the burrowing of organisms, can blur layers. Worms and other creatures mix sediments, smearing boundaries. In marine limestones, burrows can be filled with different material, leaving mottled textures. These structures are small, but they tell you about ancient environments. They also remind you that the rock record is not purely physical. It is biological too. Life is constantly editing the sediments as they form. And after the KPG boundary, life reorganizes, and those changes show up in microfossils and sediment textures. In the oceans, calcareous plankton communities changed. Certain groups declined sharply. Others expanded later. On land, plant communities shifted, and pollen records reflect that. So the boundary is not just an impact marker. It is a biological marker. A line where ecosystems changed their caste list. Now, if you want a gentle way to hold that idea, picture a shelf of old books. The spines change color gradually from volume to volume. Then, one spine is abruptly different. That is the boundary, not the end of the library, just a sudden change in the sequence. Now, your mind is ready to wander, still within the comfort of sediments, into how geologists actually handle the practical work of building a timeline. Because beyond the poetry, there is always method. You take samples at regular intervals. You label them carefully, because the label is the memory. Without the label, the rock becomes just a rock again. You measure microfossil assemblages. You measure isotope ratios. You measure elemental concentrations. You compile them into plots, depth on one axis, measurement on the other, and you look for transitions. Sometimes the transitions are smooth. Sometimes they are sharp. When you find a sharp transition that appears in many places at the same relative position, you suspect something global. That is why the iridium anomaly mattered. It was not just one outcrop, it was multiple. Then shocked quartz showed up. Then spherules. Then, eventually, a crater with the right age and size. The story became coherent. Now, coherence is not the same as simplicity. The end Cretaceous world was already stressed by other factors. Large volcanic eruptions in India, the Deccan Traps, were happening around that time. They released gases, built thick lava flows, and influenced climate. Sea level was changing. Ecosystems were evolving. So the boundary is not a neat single-cause event in every detail. But Chicxulub is a major driver of abrupt change. And the evidence for the impact is not a vibe. It is mineral physics, geochemistry, and crater structure. So you can keep the tone calm and still respect the rigor. Now, with all of this layered into your mind, you are positioned to appreciate a final, quiet pivot that geologists love. The planet's sense of time is not like yours. You think in days, years, lifetimes. The Earth thinks in deposition rates and erosion rates. A millimeter per year becomes a kilometer in a million years. A slow subsidence becomes a basin. A gentle uplift becomes a mountain range that will later be sand. And once you start thinking like that, Chicxulub becomes less of a singular horror story and more of a point on a long timeline, an interrupting layer, a structural anomaly, a moment of shock, then a long return to carbonate routine, which is why you can lie here listening and not feel overwhelmed, because deep time has a way of absorbing even sharp events into a wider rhythm. And there is still more to read in those layers.